Two important tools for analyzing behaviors. We'll start with the length of a vector. We've talked about it, but we've never actually defined it. We'll start in R2, where things are simpler. A vector pushes one point to another, and we break it into its two components. V1 in the I direction, V2 in the J direction. To get the lengths, let me take that vector and just move it out of the way for a minute to make it easier to look. And now I'll draw a triangle. So now I'm using lengths, not vectors. The length of the hypotenuse is the length of the vector, and we have the Pythagorean theorem that connects the two together. For R3, we're going to do a similar construction. 2 points, push one point to another. There's my vector. There's the shadow it casts in the xy plane, giving me the I, j components. So the vector in the plane and the vector in the k direction. V3 in the k direction, and the vector we just drew in the xy plane. Make a triangle out of those vector lengths. The horizontal one is one we just did, and the length of v is the hypotenuse. Pythagorean theorem again. Length of a vector, sum of the squares of the components. Now let's go on to projection vectors. We looked at them and we've kind of hand waved them, but we've never defined them. We'll start with the unit vector, and we want to cast the shadow of v on that unit vector. So I need to stretch out that unit vector to be the shadow that v casts. This is the definition of the dot product, is that shadow scale. Draw our triangle. The dot product is length v cosine theta, because the length of the unit vector, of course, is 1. In the special case that the unit vector is actually in the v direction, that means theta is 0. So the scale is just the length of the vector, which is v dot, the unit vector, multiply both sides by the length. And there's our dot product definition. The length of the vector squared, sum of the components squared, so that's v dot v. This now motivates our definition for dot product. If we take two vectors and dot them, multiply their components and add. With this definition for dot product, all the geometry we've done follows immediately. We use the dot symbol because the algebra of the dot product is the same algebra as multiplication. Let's put the dot product into our tangent plane construction. I start with a point in the xy plane. We're looking at the special case z is a function of x and y again. Then the z component puts it on the surface. The tangent plane, I push to the point. I take my tangent vector in the I direction. I take my tangent vector in the j direction. A point and two vectors gives me a plane, and I have my tangent plane to the surface at that point. My two vectors, in terms of partial derivatives. Now, given any other vector in that tangent plane, that is a tangent vector to the surface. And it's just a scale of these two tangent vectors. Well, then the shadow that red vector casts in the xy plane, S1i, S2j. Writing down the red vector, S1 of the first tangent vector, S2 of the second tangent vector. Collect my vectors together. The k component of the red vector is a dot product structure. The dot product of these two vectors in R2. So we'll define the gradient vector as this vector of partials. The gradient dot u is the k component. But the gradient is the vector in R2. The dot product is its projection onto that green line if u is a unit vector. Scale it back to be a unit vector. It's the same green line. Now, that distance is u hat dot gradient. Which is the length of the gradient cosine theta, where theta is the angle from the gradient to the u vector. In this case, obtuse. If theta is 0, that's your maximum positive number. If theta is pi, that's your maximum negative number. Uphill and downhill, positive and negative k component. In between, at pi over 2, 0. This is a special case and it has a special name, orthogonal. We say u hat is orthogonal to the gradient. An important construction to take away from this. The red tangent vector has this abbreviated form. So I'm scaling for unit lengths now. Scaling so that the red vector's projection is unit. Take all the green points and lift them onto the surface. That red vector is a tangent vector. And its projection in the xy plane is length 1. We will use this construction often, so it's good to understand it.